Hello, my name is Keigo Katayama. I will talk about experimental investigations of the 6-hour stability of freestanding temperature and Pitot total pressure in an incompressible decaying turbulence with tunnels. Wind tunnel experiments on incompressible turbulence are essential for testing fundamental physics and validating measurement techniques. Non-equilibrium decaying turbulence, such as grid wakes, has long served as a standard test bed. Turbulent fluctuations are commonly measured using constant temperature hot wire anemometry, which assumes steadily free stream temperature. Even small temperature variations modulate the hot wire output voltage through King's law, introducing systematic errors in velocity, conversion, and calibration. Accordingly, methods for recalibration and temperature compensation have been proposed in 2025. The Pitot total pressure, providing the reference for the freestanding speed, can also drift slowly due to fan operation, gradual temperature changes, and static pressure fluctuations. Reliable estimation of turbulence statistics with long intermittency, such as higher order moment and extreme events, requires continuous operations over several hours, for example 6 hours. However, systematic evaluations of simultaneously long-term stability in freezing temperature and pitot pressure remain limited. The stability of freezing temperature and pitot pressure directly affects hot wire signal conversion and turbulence statistics in compressive decaying turbulence. Because the sensitivity of the calibration curve depends strongly on temperature, small fluctuations introduce measurement errors. Likewise, snow drift in total pressure influences the low frequency content of non-Gaussian fluctuations. Continuous acquisition over 6 hours requires defining the time series stability of temperature and total pressure, cumulative error, recalibration intervals, and correlation validity. Conventional calibrations based on within 60 seconds records are insufficient since non-Gaussian statistics converge over longer time scales. Accordingly, this study quantifies allowable variations in temperature-sensitive hot wire conversions and vital pressure reference during 6-hour measurement, aiming to establish a quality control framework for long-duration data acquisition. Experiments are conducted in an open-circuit wind tunnel with turbulence generated by fractal grids, excluding cases with monotonic temperature rise. Wind tunnel test section had a length of 6.5 meters and a square cross-section with a side length of 0.4 meters. The center of the grid was defined as the origin of the coordinate system, and the stream direction was aligned with the tunnel axis. Was generated by a fractal grid installed normal to the flow, producing multi-scale grid turbulence as the flow passed through it. The grid had a self-similar geometry based on squares with blockage ratio of 0.32, a fractal dimension of 2, and 3 iterations. Differential pressure was measured using a Pitot tube and a bell-type differential manometer, and temperature was measured with a STEM thermometer traceable to the National Meteorology Standard. Using readings from both differential pressure instruments reduced the influence of the measurement error of any single device. All differential pressure instruments were calibrated by absolute method with dead weight before use. Measurements were taken at the location of 4,000 millimeters downstream of the grid on the freestream center line, recording temperature and differential pressure every 10 minutes for a total of 360 minutes. The laboratory was air conditioned and stabilized for 2 days before the experiment to ensure that the room environment would not affect variability inside the tunnel. The generated turbulence was characterized by its non-equilibrium, decay, and multi-scale nature, which were analyzed using frameworks consistent with previous LES and coherent structure method. This design ensures comparability with prior studies of energy decay and spectral behavior in grid turbulence. Figure shows the time series of freestream temperature for A 60 minutes and B 6 hours. Each panel each, each panel includes the mean value over the interval. In the 60-minute case, deviations are within plus minus 1%, typically plus minus 0.5%. Over 6 hours, deviations remain within 1%. Slow variability slightly increases due to slow air conditioning fluctuations. According to King's law, the square of the hot wire voltage depends on temperature. Hence, applying a time-dependent recalibration can reduce the long-term variability. The figure presents the freestream Pitot pressure over 60 minutes and 6 hours. Each panel shows the mean and plus minus 1% reference lines. During 60 minutes, the pressure is nearly consistent with a 0.2% variation. Over 6 hours, it stays within plus minus 0.5%. The amplitude of pressure variation is smaller than temperature variation. Since the hot wire voltage squared is a function of flow speed, the speed variability influencing calibration is about half of that due to temperature. Thus, a time evolving calibration curve effectively compensates for temperature drift. The figure compensates the relative RMS of the freestream temperature and Pitot pressure. For temperature, the RMS is within 0.25% for 6 minutes and within 0.4% for 6 hours for pressure, within 0.1% and within 0.2%. Hence, temperature fluctuations are roughly twice those of pressure. Because pressure scales with speed squared, the RMS of speed is within 0.1%, showing that speed variability entering King's law is negligible, and that temperature dominates calibration drift. The figure shows the 6-hour freestyle speed from Pitot to pressure. Variations stay within ±1% of the mean and are within 0.2% comparative to the background level of the tunnel. Therefore, the recalibration procedure using simultaneous voltage and speed measurements operates reliably, and the reference speed uncertainty is not a major contributor to total measurement uncertainty. This study investigates from a measurement uncertainty perspective how 6 hours of continuous operation in an incompressible decaying turbulence wind tunnels affect hot wire velocity conversion and turbulence statistics through the joint stability of freezing temperature and Pitot to the pressure. The constant temperature hot wire calibration is highly sensitive to temperature deviations, so small fluctuations cause error, while slow drift in total pressure can bias the low frequency content of non-Gaussian fluctuations. To enable long-duration measurements, the study defines stability requirements, cognitive error, recalibration intervals, and correction validity, establishing allowable variation limits and control framework. Experiments were conducted in an open circuit tunnel with a 6.5-meter test section and a 0.4 square cross-section. A fractal grid mounted normal to the floor generated multiple scale turbulence with a blockage ratio of 0.32, fractal dimension of 2, and 3 iterations. Differential pressure was measured with a Pitot tube and bell-type manometer, and temperature with a traceable stem thermometer. All pressure devices were calibrated with dead weight. The freestyle temperature remained within ±0.5% for 60 minutes and ±1% for 6 hours, showing slightly larger variability than the freestyle speed, which can be mitigated by time-dependent recalibrations. The freestyle Pitot pressure fluctuated within ±0.2% for 60 minutes and ±0.5% for 6 hours, smaller than the temperature variations. Based on RMS estimates, the corresponding speed fluctuations were about 0.25%, comparable to the background freestyle variability. Thank you for listening.